So it's my pleasure today to introduce for us our speaker, Nathaniel Starkman, who is joining us from MIT. He got his PhD at Toronto, and he did his undergrad at Case Western, and so he now still has a visitor appointment there, but he is now a Brinson postdoc fellow at MIT, and has basically like branched out from studying the Milky Way and sort of streams and tidal streams around the Milky Way to also now studying them around external galaxies using deep imaging data and randos from the internet. And I think he's going to tell us a lot about that work today. So it's been a pleasure to have him visiting us today. And I think there's maybe another slot for dinner, question mark? Sure, there's another slot for dinner. So if you'd like to go to dinner with him, talk to Ray, he's in charge. He's the oldest person in the room.
All right, thank you very much for that warm introduction and for the invitation to be here. It's really a pleasure. My first time in Texas, and I've enjoyed everything thus far. Everyone seems really nice. So hi, I'm Nathaniel Starkman. I am at MIT with a Brinson and a joint deployment at Case, but I'd also like to shout out that I do a lot of work as one of the core developers for Astronomy. So if you have any interest in developing, contributing, questions about using, I'm very happy to answer any and all questions that you might have about that. So I'm excited to tell you a bit about our ongoing work to find and characterize extragalactic stellar streams as a group that we've called ourselves EGGS, Extragalactic Gravity from Streams. You have to have a snazzy title. I think we spend more time thinking of the title than doing the work, and that's the balance. We're hoping to add some people, in fact, we are adding some people that work on shells as well, so that actually makes this a perfectly acronym. Yes. Yeah, so it's the extragalactic gravity from streams and shells. Just so double duty. Thank you. And so we've found and characterized these streams, and we're going to use them to learn about the morphology of their host galaxies. And then from there, once you have enough galaxies that you know the morphology about, right across a cosmologically relevant sample, you can start to ask and maybe one day answer some of the questions about cosmology as well using these methods. So I'm excited to tell you about that. There's a wonderful set of collaborators that we've been doing this work with across many institutions: Joe Bovey, Lena Nacheeb, Jake Neubauer, Sarah Pearson, myself, Mike Walmsley, and Suri Wu across U of T, MIT, Princeton, and collaborators in Copenhagen, where I was just recently visiting. So I always like to start with the TLDR and stellar streams, right? We all work across a pretty broad spectrum of things. What is a stellar stream? It is actually a pretty simple object, but there's a lot of rich information contained within it. The idea is that in a tidal field, like sourced by a galaxy, so this is a beautiful image of a galaxy, you can have a progenitor. This can be something like a dwarf galaxy, which is what I'll be talking about, or if you're a little closer to home, then you can see some of these globular cluster progenitors, and those end up having even prettier stellar streams. And so in the presence of this tidal field, the progenitor can disrupt. And I'm not going to talk too much about the disruption process, right? You basically have stars leaking out primarily from the Lagrange points. They have relatively low peculiar motions relative to that of the progenitor, and so you end up forming these nice orbital structures that are quite elongated. We call them streams, and that's what they are. Most of the time, you don't observe the progenitor, at least in the Milky Way. Sometimes you are lucky and you get to see it, and all you have left is this remnant of the dissolved progenitor system. And if it's dissolved in this nice and gentle way, rather than like coming in and getting smashed apart, then it can form this beautiful stellar stream. And so this is then another view of that happening. This is a great video made by Adrian Whelan back in the early 2010s, showing this happening for a globular cluster-like system. So on the left here, we have an XY galactocentric plot showing a very simple potential for a Milky Way-like system, a disk and a central bulge, and there is an NFW row in there. and you end up forming the stream from the dissolving progenitor. On the right, we are following the system right in a co-moving reference frame. And you can see what I was just sort of quickly alluding to, right, that the dissolution primarily happens from these Lagrange points, particularly for a globular cluster, and you end up forming then the long orbital structures, which we call streams. Now, in this type of idealized simulation, you'd actually never get rid of the progenitor, so it's not particularly realistic in that case, but in more realistic simulations like N-body and stuff, you can pretty rapidly destroy whatever it is that is forming the streams.
The streams themselves last for that many orbits?
Yes. So globular cluster streams in the Milky Way are generally sort of order 3-ish gigayears, but they're sort of most prominent for only a couple barycenter passages. So something like Palomar 5, which is one of the most prominent globular cluster streams, is probably gonna mostly end up disrupting, at least in terms of its progenitor, on the next barycenter passage, and then it will only stick around for maybe 1 or 2 more. So yeah, they're definitely sort of transient phenomena in that sense. Dwarf galaxy streams can last of order 5 to 6 years. So you get some more passages. Of course, it lasts longer the further out one is, where then you're increasing the amount of time that an orbit takes. All right, so the first stream was found in around 1974 with the discovery of the Magellanic Stream. And then it wasn't until nearly 20 years later that the Sagittarius Stream was found, although I have been told that in my literature review that there's actually a detection of this even a couple years earlier. I haven't hunted down the citation of it yet, but this is the rough order of the timeline for that. The first extragalactic stream was actually found, as far as I can tell, in the year 1998, NGC 5907. But it didn't seem to make a big splash, which is remarkable to me because stellar streams are really hard to find. And so finding one outside of the Milky Way would be very exciting. But kind of really the two things that really kicked off this field of stellar streams and the related dynamics happened in the year 2001 with the first discovery of a globular cluster Milky Way stream. And that was Palomar 5. And in 2001, a very lovely rich detection of a extragalactic stream. And since then, the field has just been sort of kicking up into overdrive. We've had hundreds of papers on well over now 100 streams just in the Milky Way, and not yet published by myself and then other groups that are analyzing legacy data and then Euclid data incoming. Other people are sort of reporting there's going to be of order at least 1,000-ish streams coming in from these extragalactic systems. So this is a rapidly burgeoning sector of galactic dynamics. All right, so that's a little bit of the history of streams. And I said how they formed, but why do we care? Like, okay, so these things happen, what are they good for? Depending on what type of thing you're interested in, stellar streams are nice laboratories for a variety of different questions. You can learn about the progenitor dynamics. Globular clusters are still a little bit of a mystery. How do they form? Why don't they have dark matter? Dwarf galaxies, of course, are interesting objects in and of themselves. And so looking at the dissolution process is part of their story. If you're in the Milky Way, the data is rich enough, which it just is starting to be, then you can start to learn about the subhalos, the substructure, whether that's baryonic or more exciting, at least to me, is looking at the dark matter subhalos. Stellar streams, right, there are these beautiful elongated thin structures. What that means is that they're kinematically cold, right? They don't have much dispersion to them, at least globular cluster ones. But if you hit it with a subhalo, that imparts some energy into the system. This is called heating. And so you can puff up, you can increase the width of these systems. If you hit it with a large enough thing, you can even form a gap, just so you come in like a wrecking ball and just move all the stars out of the way. And so streams then are a really excellent opportunity to study larger mass subhalos, things that are 10 to the 7, 10 to the 8, 10 to the 9, that may have impacted streams like GD1 or Uma. But then also the whole much longer tail of lower mass subhalos as they are heating up streams. But the one I'm going to be talking about is the large scale structure on the scale of the galaxy, both baryonic and dark matter. And here again, streams are really useful probes. And I'll explain more in a second, but just to give sort of an idea about why would streams be so good? Well, it's because the progenitor, right, is following an orbit. And the orbit is uniquely determined by the gravitational potential in which it's orbiting. Unfortunately, we don't get a chance to observe the orbit, and not unless you plan on living for a couple 100 million years. But what we do get a chance is to look at systems that are an ensemble of nearly an orbit. So a stream leading stars out from the edges like this, as you trace the stream sort of to 0th order, it is just an orbit. To a higher order, there's of course corrections because it's, when you bleed out stars, you don't bleed it out at exactly the location of the progenitor, right? So there's offsets and stuff. But to 0th order, a stream is an orbit. And we can then model and explain and understand those differences. And so because we're looking at something very closely related to an orbit, that means we're looking at something that's very, very sensitive to the large scale distribution. And so that's why streams are so exciting, not only for studying the dissolution of their progenitor or the way in which they're impacted by all this stochastic structure, but also the large scale structure in which they live. You can learn about the baryons and the dark matter. So that was what excited me and got me into streams when I was doing my PhD. But when it came time to think about postdocs, I kind of had the simplistic thought, what if I just multiply by a large number, right? Rather than looking at just the Milky Way, what if I looked at every single galaxy I could try to get my hands on? And so that's what I'm going to be talking to you about today, attempting to ask the question, what can we learn from an ensemble of galaxies that host streams? What can we learn about their dark matter? And another thing that motivates this, of course, is when you have understandings about individual galaxies, right, the connection between galaxies is cosmology. And there's all sorts of interesting predictions in cosmological models. And this is just a plot showing from Olga 2006, the dependence of S is a flattening parameter related to the shape of the dark matter halo to the radial mass of the systems. And so the idea is that in this, he's demonstrating that across different galaxies at different masses, you would predict and expect systematically different shapes of the dark matter. But that's true not just of the mass, it's also true, of course, with the redshift, you have evolution of galaxies over time. And you also have environmental dependencies, field galaxies, things that are well aligned with the cosmic web, large scale structure. All of these you have, in simulation at least, we have expectations that they should be impactful on the shapes of galaxies. So if we can start measuring the shapes of many galaxies, then we can maybe start answering some of these questions that have, predictions that have come up in simulation. So one of them, for example, is that you expect Milky Way halo masses to be mildly flattened at oblate at late times. All these are exciting predictions, but they've been not as thoroughly tested as we'd like, right? There's been something where simulations have been leading observations for a while now. It's very hard to do this, and I hope to show you that we're starting to do that. All right, now I'm going to be done with some of the intro and start working into some of the meat of it. I'd just like to say that I please welcome any and all questions during. I know sometimes it's the practice to wait for questions until the end, but please do not hesitate, jump in, ask me anything. I'm very happy to do that. In fact, I need it. I purposely designed the number of slides anticipating there to be questions. If you don't ask, we're going to be done very quick. All right. So this is an exciting time to be doing extragalactic things. Euclid is set to see thousands of streams, maybe tens of thousands. It's hard to do exact counts It's a little bit hard to understand how well our low surface brightness analysis pipelines are going to be able to do, but the short of it is we're going to see a lot. And even with upcoming telescopes and stuff, we're going to see even more. We're going to push down to lower surface brightness. We're going to push further away from the host galaxies. We're going to see streams and other tidal features spanning many thousands to tens of thousands in number count. And that's really exciting. This means we're going to be able to do real interesting sort of deep statistics about all of that. Of course, the trick is going to be to find them, not easy, to characterize them, still not easy, and then to use them to understand the morphology of the host. And so this is where we were struggling to do this with machine learning, and it's still an ongoing and active problem. And so we decided to turn to the internet for help. So this is a partnership between Euclid and Zooniverse, which is a citizen science platform where people can look at images and then help us perform classification. And also through an experimental platform, which I'll talk about, perform characterization of those streams to help us understand it. We're able to aggregate all of our detection and characterization over many people across the internet, which of course helps us correct for some people are better at this than others. And that's an important thing to be able to understand and filter out the people who are less good at finding and characterizing these systems. Okay, so part one is finding galaxies with streams. So finding galaxies isn't easy. As far as we can tell in Euclid, sort of fewer than 1% of streams, perhaps significantly less than 1%, of galaxies have visible streams. This actually isn't a plot made by myself. This is made by the wonderful David Ortiz Delgado, who's been doing this work of finding extragalactic systems for the past 20 years. Dedicated work, actually using a lot of amateur observers where they point nice DSLR cameras at the sky and take really long images. And they've been finding in a number of systems that are very close by some of these absolutely gorgeous stellar streams. So we thought that is great. The amateur angle appears to be very successful. Let's scale it up to Euclid. So this is an internal pilot study that we're running. Sorry, it was an internal pilot study. Now it's an actual running full-on study, citizen science on the Zooniverse platform, where we've crunched through now 20,000 identified images, finding around 100 streams, and we're going to just keep on working through Euclid Q1, and then the next releases of each. DR1 is going to be coming out relatively soon. So how do people find a stream? Well, it's actually a very simple yes/no question. They're shown an image like this one and asked, is there a stellar stream in this image? And then they click yes or no. And following the tutorial in which the answer to this is probably no. Right. But then we get to see everyone's votes across hundreds of votes. And we get to do a sampling of them ourselves for expert analysis, and then we can correlate performance and then understand who's answering the questions well, who isn't answering questions well. So this one's probably a no. I don't really see a stream, at least not one that I would be comfortable arguing is there. There's nothing distinct from the central galaxy, right? So some fraction of people would answer yes, but what's I think kind of perpetually surprising, but appreciated to myself is most people are quite good at this. It's surprising, sort of like the 75%-ish level. When there's something pretty obvious like this, people are like, yeah, there's not a stream here. And that's really good. That's actually better than a lot of ML classifiers. It's been very good for winnowing down the data. So if you were to join Zooniverse and look at the program, then you'd be presented with this very simple yes/no binary classification, help us churn through the whole data set. Then we'd aggregate it out to learn which systems are most likely to have streams.
Yeah, actually Euclid data?
Yes, this is Euclid Q1 data. we have an agreement between Euclid and Zooniverse to be able to show people anonymized images. Yeah, there's a mess of bureaucracy, but it's worked. Yes, absolutely.
So if people are bad, you just like fire them? What do you tell them? Like
You
you,
downweight them.
okay,
Yeah,
their choices don't matter.
you are there. Everyone is always appreciated.
Okay.
To join. Yeah, if you're not good, then you're weighting tends towards 0. Yeah.
Could you, sorry, this is maybe like an off the wall question, but like when you were talking about this is like, okay, low surface brightness features, looks like moderate distance from their galaxies. Like Euclid wasn't the first thing that came to my mind. I was like, why Euclid and not like HSC or something?
Yeah.
Through like these super deep images, low surface brightness. That's kind of like in my head. So I think
Yeah, absolutely. One is going to be this like all sky shear volume. Once we can get ML and stuff working for finding systems, that's going to be actually feasible to process the full sky. Other is we are seeing galaxies out to redshift 0.4, 0.5. So we're seeing systems with streams that are nice and deep, which is the lever arm we need to start doing cosmology. And then also we view training ground for future missions, which will even be even more suited for some of this surface brightness science. So we're trying to build the pipelines, get the shops, so to speak, to continue doing data sets. But I showed streams that weren't in Euclid. And I just want to show one that was found by volunteers of a system, and I think you may be hard to see with the overhead lights, which is why I think, yes, I did. But now, of course, you can only see the line that I drew. But trust me, there are stars, even if it's rather diffuse underneath this, showing a stellar stream. And I show this one because it's kind of sort of similar in terms of the morphology of the stream, that's and the sort of general relative orientation to the disk of the galaxy, to show that what we're finding in Euclid is pretty comparable to some of the really excellent, careful, deep work done by people like David Martinez-Delgado over the past 20 years with some of this, deep, careful photometry. So this is something that was found with citizen science in Euclid data sets versus found, I guess, by these more dedicated programs. So obviously, we're never going to be competitive with the depth of the data on those individual systems, but what we're going to get is volume. All right. Okay, so I'm just showing here some of the systems found by citizen scientists over the past, even actually, I guess, a couple months. And I'm going to be mostly talking about this one. It's because it's very, very pretty and always nice to show. But even though streams are relatively rare, it's been pretty amazing to see that the internet, it really can help us find systems from redshifts 0 to 0.5. And hopefully once the LSB pipelines developed by Euclid and by other people start coming out, that will have images that we can show people that are even more suited to finding lower surface brightness streams rather than some of these most prominent streams, which are all sort of close in dwarf galaxy systems. All right, so we have a pipeline for finding streams. Now comes part 2, characterizing them. So here too, we actually are turning to the internet. I popped up this showing the Zooniverse pipeline of people being able to do solar stream identification, but there's a little blue box at the top there pointing to the experimental platform, which we've developed in conjunction with Zooniverse. They're looking to expand out of kind of like yes, no, or multiple choice questions and actually be able to use more detailed user input. So things like drawing on images and stuff like that. So one of our collaborators, Mike Wamsley, did this work building out the experiment platform. And we're one of the first projects to be using it, where in addition to finding streams, people can then also characterize them. So let me show you how that works. So this is a video of myself looking at the pretty galaxy that I said, and I'm going to annotate the stream that I'm seeing on this image. It helps to be in a dark room, right? Some of the low surface brightness. So you can see that I'm drawing here sort of 3 segments. In all probability, this is actually all the same stream, dwarf galaxy stream wrapping around the galaxy, but it passes in front and behind the galaxy, and it's not particularly visible in those places. So in this annotation session, with myself standing in for someone on the internet, I did it as 3 segments. We've shown the stream to people on the internet, and not only do they see 3 segments, but very often they see 2 or sometimes 1. They actually then do that like interpolation. Or maybe they're in a very dark room and they're flipping their screen colors, and sometimes you can then pick out in reverse color some of these. So we get a spread in terms of the annotations, both spatially, but then also in terms of like number of segments. And one of the things that we're currently working on for building out a larger stream catalog is figuring out how to do this annotation fusion of all of the different annotations that people are giving us. But so this is what we see coming out, and we get the data from this, which is then another component of this citizen science that we've had the internet help us with these past months. And so now we're actually ready to start using them. I'll explain a little bit more what using them means, but for this, I'm just going to start using a simpler track annotation, which was one that is 2 segments, not 3. Right, so we have people that are just like drawing where the stream is, but now we need to understand the properties of the stream. And for this analysis, what we really need is not width information, which would be nice to eventually leverage, but all we actually need is the track of the stream. And so we're going to be fitting tracks within these annotations that best fit the streams that we're seeing. And that requires a couple of different things. So this is where some of the compute happens. We are going to be optimizing to fit a track that's contained within the region of the stream. So that's what I've written down here is a likelihood that part of a cost function that says that you must be contained within the stream. If your distance is outside of it, then it just scales as the distance, and then you turn that into basically a Heaviside function, but a continuous form so that you can do gradient-based descent when optimizing these tracks. So that's what TAN is good for, TAN inverse. It needs to also fit the shape of the annotation. So that simply says that you just want to be sort of following the approximate center. And then the most important thing actually is we want to fit the sort of smoothest possible representation of this track. And so that's something where we try to minimize the number of changes in concavity. And I'll just, as a sort of computational side note, it's actually a really challenging thing to do. You write down a likelihood that counts the number of concavity changes, and you go to your minimizer, and your minimizer breaks because that's something that you're just counting the number of, and you want to be optimizing. Your optimizer is computing gradients, but there's no gradients of step functions. So you have to spend a long time thinking about how to write a continuous form of the count of the number of concavities changes that you have. So that's what we spent some time doing, and then it turns out to be this integral function, which we can compute and then use in gradient-based descent to perform these really nice minimizations to find the track. And so what we end up with is these really nice characterizations of the track as cubic splines. And we can sample out the whole posterior to be able to marginalize out the dependence of any of our science on the track information here. I think that's really important because we don't want to have like anything related to like hyperparameters in the science that we're learning. We just want to be able to marginalize it out. And also shout out that we spent a long time, because we want this to scale to many thousands of systems and to be able to do this across every annotation that we come across. We spent some time making sure that this is a very fast process. So we can perform a full Hamiltonian Monte Carlo posterior marginalization like this on the order of less than a minute.
You're doing this to every single person's annotation, or you're doing this to like the average
Yeah, that's a good question.
everybody's annotations?
The hope is to do it to fused annotations, but fusing annotations seems to be a really tough problem.
Yeah, I was trying to think about how you might do that.
Yeah, presumably as some type of Bayesian hierarchical model where you categorize by the number of segments, but it's non-trivial. So the more trivial thing is you just do it to everyone, and then you don't fuse at the annotation level, you fuse at the likelihood level. In which case then it becomes extra important that you can spread you can do your compute fast and spread it over a cluster. And this is fully parallelizable, very fast, and so we can do hundreds of thousands on a cluster, minutes to hours. So this is just a sneak peek at some of the first crop of streams out of like the first 10,000 images we've shown people. Now, all of these are streams, that's for sure. We purposely included in the pipeline from finding to characterizing some things which are clearly not streams, but are title features, so that we can understand how people are reacting to and annotating things that aren't beautiful streams. But there definitely are some streams in here. Here's one, and these parts of it. Here's the one that I showed as well. And what you can see, which is really nice here, is this is colored by the stacking annotations. So you can see people identifying more confidently some features than others. So for example, in this one that I showed earlier, everyone is seeing that bit. Not everyone is seeing this bit, and even fewer people are seeing this bit. And then for some reason, people are seeing some of this bit, which is not a real bit. So this is where some of the post-processing that we're looking at is going to have to come into play. So I have a graduate student who's come from Copenhagen, the Dark Institute, to work with me for 2 months on some of the processing for this to start building out this catalog of Euclid streams. Okay, we found streams, we characterized them. Now let's start learning what we can learn from them. Okay, what does it mean to use a stream to learn about the dark matter? Well, there's many ways of approaching this. One of the sort of classical ways that you may be familiar with is forward modeling. Right? You take a model of a globular cluster or a dwarf galaxy, you add in a model of how it loses stars. I describe this as like primarily from the Lagrange points. That's a statement that's mostly true only for globular clusters. From dwarf galaxies, you can lose from much more extended regions. Right? And then they evolve in the potential, and they're kind of every star is kind of independent from every other star, right? They don't feel they're kind of like tracer particles. There's not enough mass generally in the stream for you to care about that. This is a sort of complex process that people have built up in terms of the machinery for modeling stellar streams. And so this is thinking about it as a forward model. And then what you end up with is a distribution of stars in your simulation, and you can compare a simulation to observation. It's very expensive, very I guess really very expensive in terms of compute, but also memory. So you can't do much compute per one. So you need a large cluster. You need to run it for a very, very long time. And unfortunately, one of the things you also end up finding is you have this really strong dependence of your results on the sort of laundry list of assumptions that you put into modeling this. And that's unfortunate, because what we'd like, and what I've sort of alluded to in saying we can like sample out the full posterior of our tracks, is to have no dependence on all these hyperparameters, particularly ones that we don't have any means to constrain. For example, if you don't see the location of the progenitor, if you're forward modeling, you need to have a really specific model of where your progenitor is in order to be bleeding out stars into forming the stellar stream. So I'm going to take a different approach for how we're going to learn about the shape of the dark matter halo from stellar streams. And one of the ways I like to think about this is to actually think about the shape of an orbit in a potential. So this is a very classical shape of an orbit in a spherical potential. It's called a rosette. Put a star in an NFW potential, right? Just let it go, and it's going to form this sort of beautiful rosette pattern. I'm going to take that exact same set of initial conditions, and I'm just going to change the potential in which the orbit is happening. If I make it oblate, if I flatten it one way versus flatten it another way, or if I have multiple axis ratios that are, all three are unequal, or if I rotate, you can see that not only does the orbit change, of course it should because I've changed the potential, but kind of like the family, the shape of that orbit changes as well. If I were to show you an orbit that looks like this, you should be able to say, if you were a dynamicist, this is not a spherical potential. This is not an orbit which happens in a spherical potential. It's one that happens in a triaxial potential. If you saw something that looks more like this, right, you can imagine that it's possible, maybe, to, maybe not by eye, but maybe by computer, right, to write out a likelihood that says the orbit family that I'm seeing, the shapes of the orbits that I'm seeing, right, favor certain shapes of potentials. And that's what we can see here in the forward direction. I can produce certain shapes by having an orbit in a potential. But I'm saying what we can also do is do the reverse, to look at the shape of the orbit and say we can understand to some extent the shape of the potential. So let me motivate that. Yeah, please. Of course.
Could you say more about the scale? I mean, I'm thinking of just like inclination, which other than the sphere, surely all of these. I'm thinking you mean something.
Oh yeah, so this is taking like a potential and then it's applying a rotation to it, right? And so you can see that the same starting point doesn't produce something that is aligned here, but it then is aligned this way, which is the inclination angle of the rotated potential in the plane here. Yeah, so if you, for example, if you knew you had an oblate potential, then just by looking at where the orbit's happening, right, then you'd be able to read off its inclination angle as well. Okay, so let me motivate this a little bit further. Slide from another. Normally I like to remove the green and have people actually shout out the answer, but oh my gosh, it's so good. It's great. Yeah.
That's the question.
Well, it's Jeopardy. The answer. Yeah. Right. If I were to show you this, and you didn't know it was B, but you know it's B. What I'm showing here is an orbit as a proxy for a stream. The curvature factors of that stream, the acceleration field, global acceleration field, and then in red is the measures of the acceleration field at the location of the stream. And you can see this in 3 different potentials. So the question is, which potential was this orbit actually integrated in? So why would it be B? Besides the fact that it kind of aligns and it sort of looks nice, actually is the reason why. If you're forming a stream, which is like forming an orbit, and you're in a static potential, then the orbit is always following, right? It's a tracer of that potential. So the acceleration field and the curvature of the orbits, the curvature of the stream, are always relatively aligned. If you were to ever misalign strongly the acceleration from the orbit or the acceleration from the stream, right? Well, you can't do that for an orbit, you can do it for a stream. You would very rapidly destroy the stream. And so basically as a survival argument, if you see a stream and you know that this potential isn't varying on very fast timescales, like didn't pass by something like an LMC very recently, then you know that all of your acceleration and curvature vectors have to be relatively fine. And so potential is the only system of these three that I've shown in which that's true. It's the only one in which this stream could have formed. Right? So this is relating the shape of the stream, the morphology of the stream, to the morphology of the potential, which is very similar to what I showed here, but now this is going to be a mathematical basis from which we can write down a likelihood. So I'm just going to show it for this system. Right, this is a well-motivated, good choice of global potential. You can see that the track in red, the blue is the local curvature vectors of that track. The green is the local acceleration field of the global potential there, and you can see that absolutely everything is aligned. So we've gone from identification to characterization, and now to analysis, where we can show that we can use the measured curvature vectors in the image plane, propose a potential, and then quantitatively assess based on the relative agreement of the measured curvature vectors and the proposed acceleration field, how well these two fit together.
Like even in that example B that you had, there were some of the vectors, right, where the local acceleration and the curvature were different, right?
Yep.
So now you're basically going to say, okay, well, now I have to adjust my potential until they are all
Yeah. So
as aligned as possible, I guess.
so you can, you want to maximally align them. There's a sort of physical threshold of 90 degrees beyond with which we accept. If they're further away than 90 degrees, right, then you rapidly destroy things. If they're closer than 90 degrees, then you sort of you're doing shifts. So they don't have to be perfectly aligned, they just need to be not misaligned. So I just want to give another shout out to Sri, who's writing up this code, which we have as an internal thing, to be a JOS paper so that anyone can do this type of analysis on their data. Hopefully we'll have a submission for that relatively soon, within the 2 months it is with me at MIT. Okay, so this is what we can learn, at least from this one of these systems. This one that I was showing before. I actually don't like showing corner plots all that much. I think that most of the marginals that we're seeing here are not the most interesting things. So I'm actually gonna just keep this in mind. I want to make a point from it, but I'm gonna break it down into specific things that we can see. What are we being able to constrain? Well, we can constrain the flattening. We can constrain the alignment within the image plane. And we can also constrain, in this model, the location of the center of mass. And then we're going to talk about that co-location with the center of light. Oh, yes, the other point I want to make here is look at my corner plots. The thing I like about it is all 4 parameters are plotted there and no other parameters. Why? It's because we had this great description of the track as a posterior. We can marginalize over all of our hyperparameters. And so unlike the forward models, where you have 10, 20 modeling assumptions that you had to bake into it, this is sort of fundamental physics arguments about the existence of streams. And we could get rid of all of our assumptions just by marginalizing them away, leaving us with just sort of constraints entirely on the actual physics that we're interested in. So that's something that we're very, very happy about. It means that our results should be relatively robust. All right. So we can learn about the center of mass. This is perhaps an obvious but true statement. You cannot get a stream to form in an orbit around something if the center of mass isn't contained within the arc of that stream. And so anytime you see an arc like this, then you end up with really strong constraints on the center of mass. So this is an example of a potential which is allowed. And this is an example of a potential that you can very confidently and immediately rule out. So the center of mass here is definitely not exterior to the center of light. We've constrained that very strongly. Of course, a little less obvious to see, but important to the model, right, is we're also sensitive to the shape of the halo, the flattening here. So what I'm showing is an example of flattened potential that is consistent with the data versus flattening that is very inconsistent data here. So from this very simple, very well motivated physics argument about the existence of streams, we're able to, on a per galaxy basis, place these types of constraints on the center of mass, the flattening, and the orientation of these systems. One of the things that we're very interested to work on is to strengthen these constraints significantly by adding more physics into this. What I'm showing here, right, is just the argument about the alignment between the curvature vectors and the acceleration vectors. There's so much more information on the table, and we think we can continue to do it without using forward models, just by doing fundamental physics, or fundamental physics, not like particle physics, but not doing prior-driven forward. One of the things that's also really nice about this method is it actually sort of treats every single point along the stream as an independent measurement. And so you can get out really good information per stream. That's something that you struggle to do in forward models where you have to model the whole system as a system. Here we can ask, what is each part of the stream telling us? In addition to that, we can even ask, where in the stream is most of our information coming from? So here I'm coloring what we're learning about the system by where in the system we are learning it. So this is sort of counting the number of times that the misalignment exceeds the threshold by which it would destroy the stream on very short time scales. And so you can see that if you allow for the center of mass to be a free parameter, that right by the center ends up being the most constraining part of the stream. So this is no surprise, right? You try to move your dynamical center of mass away from your luminous center of mass, and you very quickly run up against this very close part of the stream here. And so what we're learning is that this is then a very informative part of the stream for center of mass constraints. We can do this, of course, with, and do I have it? I think I do. I do not. You can learn where you also get most of the constraints on flattening, and that turns out to be further over here, right, where your angles are very much easier to misalign as you change the shape of the stream here. So this part of the stream is much more informative than this part of the stream, learning about the orientation. Yes.
That's interesting, but then where the stream is crossing the surface brightness of the galaxy, also one of the major uncertainties, like how do you know exactly? I mean, if you're trying to get
absolutely
believed by eye.
Yeah, absolutely. Yes, so in this annotation, right, where you trust, so this is 100% trusting the user in this case, because I drew that annotation for demonstration purposes. Right, then you'd confidently say where the stream track is. When people aren't drawing the annotation there, it becomes much more uncertain, that propagates into the uncertainty in the track. And so then you would marginalize over that as well.
Are you really dependent then on what the annotator, where the stream crosses the galaxy?
If you do this on a per annotator basis, when you fuse across hundreds of annotations. Okay, I'm actually gonna skip this because I'm starting to get pressed for time, but I'll just say that this is showing a very similar point now about where you can learn what you learn. I'm happy to talk about it after. Okay, nope, I do show it. Okay, so this is showing where we learn information when you have just the angle, the flattening and the angle in the image plane of your potential. And you can see that the endpoint of that part of the stream there is the most informative. All right, so this was showing constraints coming from a single galaxy, right? We can do this for every galaxy that we're seeing for every stream. But once you get enough galaxies, you can start asking questions cosmology, about the collections, the ensemble of all your streams. So these don't take these results with a very large grain of salt. They're from 10 galaxies. They're not even close to being realistic in that we're not going to do any type of dependence on the redshift, on the mass, on the environment, or anything like that. We're just going to pretend that all of these are from the exact same sort of like type of galaxy. We can just stack them, right? And we can consider ensemble constraints about sort of like the prototypical galaxy, the average galaxy in the universe. Right, so this was just returning back to the motivation where if you have enough streams, then you can start having these cosmological models that you constrain. But I said, I'm just gonna ask the question, not what is like the dependence as a function of mass, but what is just sort of the average galaxy that we see sort of from redshift 0 to redshift 0.5. So for that, we're just gonna stack all of the galaxies. And the really nice thing about this analysis is it's actually scale free. So if you are only using relative angles like we're using, then there's no dependence for radial information. So if you just scale all the systems to be the sort of the same angular size, then you can perform this analysis. Of course, you can't do things that are like dependence on the mass, dependence on the size, because we are literally getting rid of that information. Okay, so we can take a look at halo flattening. This is what our data from just 10 galaxies right now is telling us. It's telling us that these systems prefer a mild degree of flattening. They ever so slightly disfavor perfectly spherical. They strongly disfavor highly flattened systems, and they're enjoying a broad range, right, of mildly flattened systems in the image plane. And this is actually really in line with what we see in simulations. Of course, with more data, we hope to tighten this up so that you can actually really start telling it apart for the dependence. But this is in perfect agreement. There's no surprise. It's not saying we want really, really flattened systems. So this is a nice thing to see, at least at the 10 galaxy level, that when you stack them and you put them all together, it says, yeah, simulations are broadly correct, or work broadly correct as simulations. Depends on what you believe is more true than the universe. We can also talk about center of mass offsets in the same way. So this is asking the question, how far away from the center of light is the dynamical center of mass that we're inferring? And again, to sort of no surprise, we're finding that you strongly favor being well within the radius of the galaxy. Now, not many dark matter models predict that the center of mass would be well outside the center of the radius of the galaxy. But again, this is what we can get out with just 10 galaxies, leveraging just this scale-free information about the relative alignments of the accelerating curvature. As we theoretically advance this method, as we get more information, we'll be able to tighten up these constraints. But I actually like to call this my most boring plot, because what isn't that interesting? It's the very obvious expectation that the center of mass and the center of light are relatively close. What's really interesting is the extraordinary system, the one in which they're strongly different, the bullet cluster, for clusters. So one of the really nice things about this method is not only can we do these types of stacked analyses, but we can also do it per galaxy. That's what I was showing before, right? How we get the joint analysis is by combining individual analysis, which means that if there were ever out in the universe, and we saw it, a stream that had a very clear signal that the dynamical center of mass was strongly offset from the luminous center of the system. That is the extraordinary system. That is the bullet cluster. That is the smoking gun of dark matter. That's the one that's not going to show up in this plot. So this is the most boring plot I can show. In fact, I think it's to motivate. One of the great things we can learn about streams is a dynamical model. They can do individual systems. You don't have to stack. All right, this brings me to the conclusions. If you're a member of Euclid, you can take a look at the paper, please comment. If you're not, I'm happy to discuss anything in it. You've seen some plots from the paper. We're currently still working on scaling up, showing people many more images, working on the data rights for DR1 to be able to show them yet more, working on doing ML stream detections. We're also working on theory improvements to be able to use a lot more information in a way that still isn't sort of prior driven forward modeling. So things that are very close to the data, as close as we can be. But the takeaway that we're going to have from all of this is that this is a new, novel, fast, minimal assumption probe of dark matter halo geometries. completely independent from complementary pipelines like weak lensing, strong lensing, and other measures. And we can start applying across sort of cosmological volumes, redshift 0 to 0.5, maybe even deeper, to learn about individual systems. But not only those, we can then combine this in cosmological models to start learning about cosmology. Hopefully we'll be able to bring this all together in a unified picture with all the other probes like weak lensing and stuff like that to build both dynamical and sort of direct gravitational probes of dark matter across the universe. So I think it's a very exciting time to be doing extragalactic streams. Thank you.
For theory improvements,
Yes.
so you get more information. Is this, compared to the form modeling stuff, is this more and different information or the same plus extra?
Yeah. So compared to forward modeling, it's less than the same. But why? Okay, yeah. So forward modeling, in principle, if you had all of those values, the location of the progenitor, how it dissolves in the tidal field, if you have all of those right,
Okay.
you would get the most exquisite and perfect measurement of your stream that matches the system. Right? In practice, you can't do that. So you end up with all these sort of complicated values that are very hard to understand. In this approach, this non-generative approach, where it's very close to the data, so you have existence-based arguments, right? You are leaving a lot of information on the table, but you're not making any of those inference assumptions. Our goal is to work towards, and we are working on a theory paper on this at the moment, about how to leverage a lot more information, the curvature magnitudes, not just their width of the system, something like that. All of these are related to the dynamics of streams, and you can sort of make similar to some extent existence models and other things that are quite robust about the systems. But no matter what, you will never have as perfect a model as a forward model. We actually are like producing. But it's not gonna make mistakes.
Can you also use this offset between the center mass and the center light to figure out which of your streams might have actually just been like mergers, tidal features?
Yes, yeah. Yes, you absolutely can. Of course, the kind of the danger of doing this is it's then really hard to not find the answer that you're putting in. If you say which systems agree with my expected answer, whichever ones don't, I remove my data sets.
I remember you saying that you were like giving people some, tidal features and some
Yeah.
streams, and yeah, so I was trying to figure out like how.
Yeah, so this also actually doesn't use any color information. So a lot of tidal distinctions about what is a tidal feature versus what is a stream can be done by perspicacious observers with access to color information who know more about that than myself. So right, I think one of the things I said is we actually don't want to be in the stream discovery game. That's not something that our collaboration is that interested in. It's a space that we were forced to get in because there is no catalog of extragalactic streams. We turned to citizen science because it allowed us to rapidly scale up and build these types of data sets in a space that ML is currently very struggling in. So if and when ML classifiers advance to the point that they are reliably able to distinguish between a tidal feature like that, tumor interactions like that, and with an actual stellar stream, that's the day we'll happily move out of that space and remain just in the characterization and analysis. So remove one of our two Zooniverse active Zooniverse programs for the other. But LSST is looking to, I think, to do actually a citizen science one, perhaps in partnership with us, about stream finding, something like that, because it probably appears necessary to have at least a good training set that you can for domain adaptation. So even if you have a good classifier on Euclid data, it's not going to be a great classifier on Rubin Roman data. You're going to need some labeled sets, maybe even relatively large ones, tens of thousands of systems, to be able to do domain adaptation. So this type of exercise may be necessary, kind of no matter how good your ML is, unless you can figure out how to model not just the system that you're seeing, but also all of the stuff between the universe, the detector, all the detector stuff that's happening.
So we are at the hour, so I'm gonna say